Hello and welcome to the video lecture series on the chemistry of heterocycles. Today's topic of discussion is the chemistry of indoles and particularly the synthesis of indoles. We have only one synthesis enlisted in our syllabus, and that is the Fischer indole synthesis. So let's take it up and see what this thing is all about. Indole nucleus is a fused heterocycle, a bicyclic compound, where you have a pyrrole ring fused with a benzene. The numbering of this heterocyclic bicyclic system follows the usual convention of skipping the ring juncture. You start with the nitrogen and then you move in a fashion where you label the heterocyclic ring first and then you go on to the carbocycle. So if nitrogen is 1, then this is the 2, C2, and this is the C3, and these positions are labeled as alpha and beta respectively, as you can remember uh, for the pyrrole and furan and thiophene systems. Then you skip the ring juncture, go to 4, 5, 6, 7, and then this is 8 and this is 9. So this is a benzo-fused pyrrole ring. Indole has a special place, particularly for people from the Bengal province. The East India Company, when they were trading uh, in, in these parts, uh, and uh, they were doing business with uh, mostly commodities that were not available to England or Europe. One of those things was the indigo, the blue dye, that was extremely popular back in the continent, and they were forcing the cultivators from the Bengal province to stop cultivating any other crop and just to grow indigo. And there have been legendary atrocities in which uh, the cultivators were subjected to which the cultivators were subjected to, and uh, they were made to forcefully grow indigo. And the the indigo revolt is one of the important chapters in the history of British India. Dinobandhu Mitra wrote a heart-wrenching play called Nildarpon, where he outlined that how the Nilkors are torturing and tormenting the riots. So that's not chemistry, but that is a social commentary, social history that was associated with indigo, and the blue color of indigo was because of a compound which contained this indole molecule. Now let us move on to the synthesis. So synthesis, we will be discussing Fischer indole synthesis. The name is from Hermann Emil Fischer, the legendary organic chemist who won the Nobel Prize for his seminal work in carbohydrate chemistry, and he also uh, contributed a lot in heterocyclic chemistry as well, and one of his most important contribution in this field is the Fischer indole synthesis. The molecule phenylhydrazine was serendipitously prepared by Fischer. I mean, accidentally prepared. He was not aiming to prepare this, but he somehow managed to do that. And this molecule played a seminal role also in his life. Because of this phenylhydrazine, he could characterize several carbohydrates by forming crystalline derivatives called usazone. And with this phenylhydrazine, he also managed to synthesize indole, which bears his name as Fischer indole synthesis. And this molecule is also responsible for uh, cancer, for Emil Fischer's cancer in his advanced years, because this is a potent and known carcinogen. But at that point, Fischer did not know that, and he handled this compound freely and probably without much care, because at that point of time, this chemical safety was not considered to be that important. Not obviously as important as it is considered now. So this phenylhydrazine basically killed Emil Fischer. And this phenylhydrazine also helped him win the Nobel Prize. So that's the irony. So when you combine phenylhydrazine with a ketone with an alpha hydrogen, so you get basically a phenylhydrazone. That's a addition elimination mechanism through which you get the phenylhydrazone. Under acid catalysis, you get this phenylhydrazone. But the phenylhydrazone under this reaction condition cyclizes, expelling one of the nitrogen atoms. The blue nitrogen atom actually stays. This nitrogen atom will actually go, and you will get the substituted indole derivative. Generally, the reaction is carried out with protic acid or Lewis acid. Say you can take polyphosphoric acid or zinc chloride, paratoluene sulfonic acid, or a Lewis acid such as boron trifluoride, etc. The nature of the substituents that are already present in the aromatic ring, they have a very strong influence on the rate of the overall reaction. Electron donating substituents accelerate the reaction, while electron releasing substituents slow down the cyclization. So your mechanism has to be explained, has to be able to explain why this kind of rate profile is being displayed. So there are a few 4-5 examples that we are dealing with. You should be actually able to predict from which carbonyl compounds these phenylhydrazones or substituted phenylhydrazones have been prepared. Say for example, this is a molecule which is coming from pyruvic acid. You should be familiar with pyruvic acid from your biochemistry course. Glucose in glycolysis breaks down to the pyruvic acid, and this is the actually breaks down to the pyruvate, but this is the pyruvic acid, and the phenylhydrazone is actually N-methyl phenylhydrazone. So you have a methyl here, and you can clearly see that between these two nitrogen, it is this nitrogen which is retained because you have a N-methyl group retained here, and with elimination of ammonia. If this nitrogen were to be retained, then I would have NH here, and methylamine would have been eliminated. The reaction is done in ethanol medium in presence of HCl catalyst. This one is a phenylhydrazone derived from 1,2,3-propanal. Zinc chloride catalyzed at high temperature. The reaction is taking place. You are getting 3-methyl indole. If you do the reaction with the phenylhydrazone of acetophenone, as you can see, all the time we have something where alpha hydrogen is present, and from that side we are closing the ring down. We are getting here 2-phenyl indole. With phenylhydrazone of acetone, you can enolize, or you can exploit the alpha hydrogen from here or from here. Doesn't really matter because these are the symmetrical things. Again, you get 2-methyl indole. So you can prepare 3-methyl indole. You can prepare 2-methyl indole from using the Fischer indole synthesis. This is a versatile method, depending upon what you are choosing as your starting keto or aldehyde. This one is important for organic chemists because this is part of the legendary strychnine synthesis of R.B. Woodward, in which he took acetoviractone. You have two toxic groups at the 1, 2, 3 prime and 4 prime position of the acetophenol moiety, and you have cyclized it with phenylhydrazine in polyphosphoric acid. In situ phenylhydrazone will form, and then cyclization will take place to give you the substituted indole, which was subjected to further transformations. This was part of the strychnine synthesis. The mechanism of Fischer indole synthesis is not easy, and it took a lot of years and a lot of efforts from many different chemists to establish the mechanism as it is now. Basically, it consists of many steps, but grossly, you can divide it into three distinct stages. The first stage is the hydrazone, that means the phenylhydrazone. When I say hydrazone, I mean the phenylhydrazone. Hydrazone in hydrazine equilibrium. So the phenylhydrazone can tautomerize to an enhydrazine. That's basically a imine-enamine tautomerism. This is obviously an enamine. As you can see, this is obviously an enamine. This is obviously an imine with alpha hydrogen. So imine is nothing but as an analog of carbonyl with alpha hydrogen. So if enol form is possible for the keto or aldehyde, then enamine form is also possible for the imine. So under this acid catalyzed condition, you get the enhydrazine of the enamine form from the phenylhydrazone of the imine form. Now proton is there, then you protonate. Now you protonate this nitrogen. That means the one that is conjugated with the carbon-carbon double bond. And after the protonation, the conjugate acid of the enhydrazine undergoes a 3,3 sigmatropic shift. That's a pericyclic reaction. So that's 1,1. This nitrogen bond is 1,1. Then you have these 2,3 and also 2,3, and then you shift the bonds around so that the nitrogen bond is broken, and from with this alpha carbon you can establish a linkage with the ortho position at linkage level. After that, in normal course, you expect that the aromaticity will take place, aromatization will take place. Aromatization happens. After aromatization is done, this nitrogen is being, in the protonated state, it is making this carbon electrophilic, and this nitrogen is freely nucleophilic. So this will close down the ring. Now you have your, your cyclized product, and that's an amine. So that's basically a 1,1-diX compound. That means on the same carbon you have two heteroatoms. So after protonation, this nitrogen will help to expel this ammonium in the form of ammonia, and then one of the other alpha protons will shift so that you get after the tautomeristic change, you get your indole nucleus. So that's basically a mechanism of Fischer indole synthesis. They ask you a lot of questions about this mechanism, particularly what kind of proofs do you have, etc. So the three stages are hydrazone, enhydrazine, equilibrium. Second stage is obviously formation of the CC bond at the expense of the NN bond by 3,3 sigmatropic shift, and then closing down the ring and losing ammonia so that the indole nucleus can be reduced. If we are able to trap the proposed enhydrazine enamine intermediate, then it would have indicated this mechanism, because if this is being produced in the reaction medium, you should be able to trap it, and that had been done. So phenylhydrazone reacting with unsymmetrical ketone butanone. With butanone, you could cyclize from this side or you could cyclize from that side, but before cyclization, they have managed to trap the enhydrazine, the enhydrazine or the imine or the enamine moiety by reacting it with acetic anhydride, and you can see that the enolization has taken place from the more substituted side. But before it could get any further, the trapping agent as acetic anhydride being present in the medium has trapped the enhydrazine and formed a doubly acetylated enhydrazine molecule. This question is very popular. They ask you, how can you prove the Fischer indole synthesis by using isotopic tracer techniques? So you prepare a labeled enhydrazine where you label particularly this nitrogen, and you can do that because enhydrazine is prepared by reducing the diazonium chloride, benzene diazonium chloride in presence of NaOH and sulfur dioxide. Sulfur dioxide is actually the reducing agent. So if you start with nitrobenzene, where this nitrogen is labeled, and eventually reduce it and then diiotize it with NaNO2, where this nitrogen is normal nitrogen, N40. So you get this diazo compound where that nitrogen is labeled, and eventually the phenylhydrazine where the nitrogen attached to the phenyl ring is also labeled. And then you do the reaction with acetophenone. There is only one place from where enolization can take place. Eventually you will end up with 2-phenyl indole, where this nitrogen, that is the one that was attached to the ring, is retained, and as you can see, the N15 which was attached to the ring is retained in the nucleus. The ammonia that is coming out is nitrogen 15 free. If you do the reaction in the opposite way, that means you take nitrobenzene where the nitrogen is not labeled, and you then reduce it and then diazotize it with NaNO2 where this nitrogen is labeled, then you will end up with a phenylhydrazine where the remote nitrogen is labeled, and with the same sequence of reaction, this time the ammonia will be labeled, but the ring nitrogen of the indole, 2-phenyl indole, will be not labeled. This is one of the or two of the ways in which isotopic labeling can be used to decipher the mechanistic course of Fischer indole synthesis, which nitrogen is being lost. If they ask you to write isotopic labeling, you write any one of them. If they ask you to write give non-isotopic evidence, then this is a beautiful example. The acetophenone thing, doing this thing with N-methyl phenylhydrazine. So eventually you will end up with the N-methylated 2-phenyl indole, and ammonia will be lost, which means that this nitrogen is getting lost and that nitrogen is being retained, because if we are losing this nitrogen, then we would have got 2-phenyl indole and methylamine. Okay. Now, people have prepared inhydrazines in separate ways, and they have subjected it to the Fischer indole cyclization, and they have discovered that even without the acid catalysis, the reaction can take place, but the reaction is significantly slow, and therefore you need very high temperatures to get the proper indole derivative. Acid catalysis is necessary to carry out the reaction efficiently, but without acid catalysis you can still get some reaction. Say for example, particularly they have taken this N-phenyl N-trifluoroacetyl derivative, and they have prepared the corresponding inhydrazine in a separate manner, and they have subjected it to Fischer indole cyclization without any acid catalysis being present, So they have managed to prepare this thing with the expulsion of this particular nitrogen in the form of CF3CONH2. They have again prepared this doubly N-methylated inhydrazine from this compound. You do the reaction in absence of acid catalyst, and then again in presence of acid catalyst, the rate of the reaction for the acid catalyzed version is remarkably high. On the other hand, the non-catalyzed version, not only is it slow, but also the yield is not very good. So we are forced to say that protonation actually facilitates the reaction, and it has been discovered that protonation actually facilitates the 3+3 cycloaddition step. That happens very well, and as you can see, it is a protonated positively charged intermediate through which the reaction takes place, and here the aromatic ring would be better off with electron releasing substituents, because the positive charge actually is somehow sort of getting a little bit dispersed over the whole transition state. So in presence of electron withdrawing groups, these reactions are not very facile. In presence of electron releasing groups, this reaction is much more facile. Okay, then we have the regioselectivity, and that is a question which we will not be able to answer to the fullest extent, because that is a very complicated and complex explanation. I don't want to go over that, but if some of you are interested, please feel free to ask me about the intricacies of this, and I will point you in the right direction. So here you have butanone. Okay, just as we were talking with this example, you have two different positions from which enolization can take place. And as you can see, it can give rise to two different products. One is a 2-ethyl indole, the other is a 2,3-dimethyl indole. And if you vary the strength of the acid catalysis, then the percentage composition changes. When you are using acetic acid, the more substituted uh, uh, the more substituted inhydrazine is reacting, and we are getting the 2,3 product at 100%. Whereas as you go on increasing the acid strength from acetic acid to polyphosphoric acid and then to Eaton's reagent, the percentage of the 2-ethyl indole which arises from the more substituted inhydrazine, you get this particular product in a higher amount, and this 2,3 dimethyl indole which comes from the less substituted inhydrazine, that percentage is decreasing. I will not go into the details. I will say only these things, that increasing acidity favors the less substituted inhydrazine increasingly, and therefore people call it, this one is the kinetic product. As you can see, this is the kinetic enol and or kinetic enamine, and this is the thermodynamic product, or the more substituted, more stable enamine or inhydrazine, whatever you may choose to call it. In a similar way, if you take the inhydrazine of 2-methyl cyclohexanone, not the inhydrazine but the phenylhydrazone of the 2-methyl cyclohexanone with acetic acid, you get 61:6 ratio for these two, where this magenta colored one is coming from the less substituted inhydrazine, and the blue colored one is coming from the more substituted inhydrazine. This one cannot tautomerize, as you can see. This one can obviously tautomerize, but I have just drawn before the tautomerization step, and it will eventually tautomerize to this particular indole derivative. With acetic acid, again, the more substituted inhydrazine, that is the major product, the indole arising out of the more substituted inhydrazine. With sulfuric acid, a stronger acid, the product ratio changes, and it is the less substituted, the kinetically controlled inhydrazine which leads to the major product. Again, you have an example where you are forming phenylhydrazone by an exchange reaction. This is the phenylhydrazine of benzophenone, and now you are treating that thing with 3-methyl 2-butanone, so that you get corresponding phenylhydrazone of this carbonyl compound, which cyclizes with paratoluene sulfonic acid. It is from that side the cyclization is happening, and it cannot aromatize. It is under this reaction condition. This is going through the more substituted inhydrazine. So this is relatively weak acid condition through which the reaction is taking place, and that is why the more substituted inhydrazine is probably being favored. Okay, now regioselectivity. This is, again, I have told you, very important, because the substituents actually direct in which position the cyclization can take place. Also, they direct how much the rate will be. So if you have para substituted phenylhydrazones, then indolization will give you only one regioisomer, because these two positions are the same. So if you cyclize from that side, or if you redraw the molecule so that the cyclization can take place from that side, you will get only the 5 substituted derivative, as you can see from these two examples. And here we have taken ethyl ester of pyruvate, ethyl ester of pyruvic acid, only one place from which you can enolize. With this particular compound, you are doing the reaction in sulfuric acid medium, and it is the less substituted inhydrazine which is cyclizing, as you can see. Things will become interesting if you take ortho-substituted aryl hydrazone. Sometimes they give you one isomer. However, the cyclization is slower in comparison to the meta or para substituted derivatives, and they can occur, the cyclization can occur either from the unsubstituted side to give you the normal indole products, or the substituted sites where the other reactions take place and you get some unexpected product. So if you have a methoxy group present at the one of the ortho positions, then one of the product that you get can be the 7 substituted indole where you are cyclizing these two positions. This is normal product. This one is unsubstituted, so you cyclize, you can aromatize, etc., so on. But there are conditions under which cyclization can take place from the substituted side, and obviously this intermediate cannot aromatize. It cannot aromatize. So other things have to be done. Cyclization takes place where there is no aromaticity that can be gained by ejecting this methoxy as of now. So what happens is, if you are doing the reaction in presence of the HX catalysis, particularly if X is chloride or bromide, etc., then this can act as a nucleophile and do a SN2' reactions to dislodge this methoxy, eventually installing the X group on the 5 carbon. So that's like you get a disubstituted indole in 2-3 positions if you are starting with a butanone kind of thing, and you have a X at the C5 position. These are the one of the abnormal products. Or X minus can choose to make a Michael type, a Michael addition type reaction with this iminium. This is the alpha carbon with respect to iminium, and this is the beta carbon with respect to iminium, and don't confuse these two with the alpha beta position of the indoles. I am just trying to highlight this portion. So X minus can attack, Michael addition type reaction can take place, and then this MEOH, methanol, will go via a 1,4 elimination, so that aromatization can happen and you get a regio isomer. The 6th position, you get substituent X at the 6th position. Okay. If we have ortho disubstituted, then the indole will definitely not be able to aromatize because there is no unsubstituted ortho positions, and you get something like this. Now, before cyclization, one thing may happen. One of these ortho substituents where you have chosen to cyclize, it may undergo a rearrangement step. So that's basically a 1,2 alkyl shift, and subsequently the carbon-carbon double bonds and carbon-nitrogen double bonds are shifting their position so that this NH becomes NH2 and R shifts here so that the plus charge comes here, and this is a very unstable intermediate with two positive charges being present, but you cannot possibly cyclize at this point, because if this were not hydrogen, you cannot have a double bond here and this cannot become NH2, so this cannot cyclize. So before cyclization, you must be able to shift this R group to the adjacent carbon, and once that has happened, it can just lose the proton to gain aromaticity, and this NH2 can attack this iminium, so that cyclization can take place. So eventually you will have a 4,7 disubstituted thing. This was like, they were like in these two positions, but one of the R group has shifted on the adjacent carbons. 3 substituted phenylhydrazine, that means meta substitution, generally give rise to 2 regioisomers. If you cyclize 2 from this side, you will get the C4, or if you redraw it and cyclize from that side, you will get the C6. The ratio of that thing actually depends on the nature of the R group that is being present. If R is electron releasing group, then this product, where the cyclization is taking place at the para position with respect to R, that is the major product. And if AR is electron withdrawing group, then it is the that product, the product A, where cyclization is ortho with respect to R, that generally happens. That is the general trend that is observed. As you can see, methyl being an electron releasing group, this B product is the major product, A is the minor product. However, B is, on steric grounds, B is always favored over A. And this is a beautiful example where you can see that it is truly the electron rich ring where the reaction is preferably happening. You have in hydrazine where on this nitrogen you have 2 two different rings. The red ring is the trifluoromethyl substituted benzene ring. That phenyl ring is electron deficient because CF3 is electron withdrawing group, and the blue ring is the electron rich ring. When you cyclize in this direction using the blue ring, you get the product Y. When you cyclize in this direction using the red ring, you get the product X. Under similar condition, if you do the reaction, then this is basically asking the molecule to do a competitive reaction onto itself. So it can choose to cyclize from that side or from that side. The ratio of the product is 1:10. And as is expected, because we have already discussed that due to the presence of the positive charge inside the molecule almost throughout the reaction, the cyclization will happen, particularly the cyclization is good or particularly efficient with electron rich rings and particularly bad with electron deficient rings. So it is expected that this product will be the major product and that product will be the minor product. As you can see, 1:10 ratio is being shown. The final part of this lecture is the preparation of the phenylhydrazones by Japp-Klingemann reaction. This is a reaction which we have discussed while we were talking about the aromatic electrophilic substitution and in the chemistry of the diazonium salts, the chemistry under the chemistry of nitrogen compounds. So Japp-Klingemann reaction is a very old reaction where you can couple a substituted acetoacetic acid with phenylhydrazine, with a diazonium chloride, and that's a weak electrophile. This is basically like nitration of the enol form that you can access from the active methylene compound or substituted active methylene compound. Just like you can install a NO group here, you can also include this weak electrophile, and under this basic condition, after introduction of the electrophile, certain changes happen and you get the aryl hydrazone. So let's look into the mechanism. We have already discussed it, but let's look at it again. So the very first thing is that the sodium hydroxide deprotonates the acetoacetic acid. So you get carboxylate. This hydrogen is acidic because it is flanked by two carbonyl groups, although one of them is carboxylate, but still acidic enough to be deprotonated. At least a little bit of this molecule will exist in this highly nucleophilic double anion enolate form. The C minus is more reactive than either of these two O minuses, particularly this is very bad nucleophilic because this is resonance stabilized. Oxygen is a hard nucleophile, carbon is a softer nucleophile, so you get introduction of the weak electrophile here. And once you have that, just like if you had a proton here and that could have shifted via tautomeric change from carbon to this nitrogen, instead of proton you have a carboxylate, CO2 minus. And as you have seen on at least two different occasions, this carboxylate can behave like a proton and we can get decarboxylation reaction with the rupture of this carbon-carbon bond and formation of this C-CN double bond, and this nitrogen-nitrogen double bond breaks. This nitrogen takes up a proton from the reaction medium. Remember, you have water in the reaction medium, so you get your phenylhydrazone, and from that phenylhydrazone you can do the Fischer indole cyclization. So this time you are preparing phenylhydrazone, but you are not using the Fischer's phenylhydrazine. You are using as a source of this nitrogen, to the source of this two nitrogen, you are using the diazonium salt. So with this you could go on and do the reaction, so that you have your substituted indole nucleus. And there are 2-3 more examples here. This one is particularly interesting because this time you are losing the ketomethyl group by a nucleophilic attack of the hydroxide, and you are getting the phenylhydrazone. That's an interesting mechanism. And then you are cyclizing from that side to get this particular compound. So Fischer indole synthesis cannot directly be done. If you want to prepare indole, You cannot go for the Fischer indole synthesis between phenylhydrazine and acetaldehyde, because if you are to prepare indole from just indole from Fischer indole synthesis, then you can understand that if you have hydrogen here, then this will be indole. Okay, so for that you need acetaldehyde. With acetaldehyde, if you do the reaction, obviously you need to have hydrogen here, but that's not a problem because phenylhydrazine is available to you. But with acetaldehyde, when acetaldehyde is treated with the phenylhydrazine, acetaldehyde is so reactive and it reacts amongst themselves to give you aldol condensation product, and that reaction is unfavorable. I mean, in terms of Fischer indole synthesis, that reaction is useless. So people prepare indole by Fischer indole synthesis not using acetaldehyde but using the pyruvic acid. So they do the reaction with pyruvic acid and condense the pyruvic acid with the phenylhydrazine, so that they end up with indole derivative where you have a carboxylic acid group at the 2 position, and then they decarboxylate it. As you will see, indole nucleus can lose carboxylic acids at the C3 and C2 positions under proper reaction conditions, so that the indole, so that they get the indole itself. And Fischer indole synthesis is also responsible for the synthetic production of the indigo, which brought an end to the atrocities of the Nile course, because when the thing could be produced in factories, you don't really have to torment your riots to produce more and more of that stuff, because cultivation land cannot compete with industrial production. So in that sense, Fischer indirectly brought an end to the torture and subjugation of the riots by the Nile course in these parts of this world. So coming back to this discussion, we are losing the ketomethyl group here and getting the phenylhydrazone cyclization here, and you get the ester derivative. You can hydrolyze it and decarboxylate. This one is a pretty interesting mechanism where from this cyclopentanone to carboxy cyclopentanone, we are getting the phenylhydrazone. I urge you to look into the mechanism and check whether you are able to decipher what is happening. And then this sulfuric acid catalyzed cyclization is taking place. Obviously, this is the only position from which the hydrogen can form, and you get a CO2 here and a CO2H and a CH2CH2CO2H here. After hydrolysis, you convert it to CO2H, and then under proper decarboxylation condition, you can use this carbon dioxide to get this derivative. Finally, you have again a ketomethyl group, a beta-keto ester. That's also a beta-keto ester. Methyl, that's a methyl substituted ethyl acetoacetate. This time the substitution is CH2CH2CO2. Under the same reaction condition, you are losing again the acetyl group to give you the phenylhydrazone derivative. From enolization or enamine formation can take place only from that side, so cyclization will be from that side only. You will get this derivative where you have a CO2 here, and instead of a CH2CH2CO2H, you have a CH2CO2. Hydrolysis converts both these CO2 groups into carboxylic acids. Only the alpha carboxylic acid can be decarboxylated to give you this substituted indole nucleus. So that's about the Fischer indole synthesis. We will be taking up the reactions of the indole in the next installment of this video lecture series. I thank you for your patience, and I will be seeing you in the next one.